Measuring pressure. In order to understand gases, we measure four key variables. Pressure, title of this little unit here, temperature, volume, and the number of moles, which you should be thoroughly familiar with after the last unit. We're first going to describe how we measure pressure and temperature, so this guy and this guy, and then we will discuss the relationships between all four of these variables for gases. A key characteristic of gases is their pressure, which is the force that they exert on their container. And pressure is the force applied per unit area. You may have come across this in physics or in middle school or somewhere, but this is a key equation. Pressure, force per unit area. The SI units, or the standard units of pressure, can be determined from looking at the formula. Force is measured in newtons, named after Sir Isaac Newton. Area, measured in square meters. Another way to show that is meters squared, like this. So the unit is newtons per meter squared. But that's a lot to say, so it was renamed, or it can also be called a Pascal, named after Blaise Pascal, a French physicist, a Catholic theologian, a mathematician, a writer who lived in the 1600s. Kind of did everything. So you can either say newtons per meter squared or just call it a Pascal. The same force can result in very different pressures. Why is that? Well, pressure is force per unit area. So if you have the same force, but you vary this area, and the area is the place where you contact the other object. So let's look at this. What's the pressure that the chemistry book exerts on the table? It's got a large surface area because it's sideways, so that will have less pressure than if you turn the same chemistry book on its edge, so it has a smaller surface area that's contacting the table. The smaller area means A goes up, so the pressure goes up. So there's more pressure exerted by the same book in case 2 compared to case 1. Perhaps you've heard the term atmospheric pressure when you listen to weather reports. Well, here's a definition. It is the weight of the air per unit area. So if you take a square meter column of air and you extend it to outer space, right here, see this parallelepiped or three-dimensional cube? Three-dimensional rectangle, sorry. A square meter column of air extending to outer space has a weight, the air in here, you add up all that air, of about 101 kilonewtons. At sea level, it will exert a pressure of 101 kilopascals. All right, we just divided the force by the area. We're going to call that 101 kilopascals 1 atmosphere. If a mountain climber ascended to 20,000 feet, he's halfway up. You've got half the atmosphere above him, half below. The pressure he or she feels, will be 50 kilopascals. Okay, that's half. Half of the atmosphere is below the level, so there's less pressure. Inside a gas, the pressure acts in all directions at a given point. See, there's a little cube of water here. Since there's no direction associated with pressure, it is a scalar quantity. If it had a direction, it would be called a vector quantity. Now, when you get to the surface of the gas or at the surface of the container, pressure acts in a perpendicular direction. Okay, so the gas would be exerting a pressure this way, perpendicular to the container. The gas would exert a pressure this way, perpendicular to the surface, and if there's air up here, it would exert pressure perpendicular to the surface of the gas. A force of 300,000 newtons is equal to about 13,000 pounds. And let's say it's being exerted on this table. Why doesn't the table collapse? Why doesn't it do that? Okay, we'll take a second to think about it, then we'll pull out the answer tab. Well, in this case, the gases are exerting their pressure in all directions like we talked about earlier. Okay, so the table, the force pushing down on the table, is opposed by an almost equal force of air pushing it up from below the table. There's a slight difference because it's a little bit lower, but it's pretty much the same. If you were to take away this air here, the table would collapse. There's a great little physics demonstration where you have maybe something about 12 inches by 12 inches, and it's a little rubber thing. And on top of it you have a hook, and it's a thin rubber piece of paper. Maybe it's a little thicker than paper. You put it down on a surface and you cannot pull it up because the pressure of the air is pushing down on it, and there's nothing pushing up because it's resting on a table. So the trick is to slide it over to the edge of your table so you get that air pressure from the bottom pushing up, equalizing the forces and enabling you to lift it up. The barometer. Perhaps you've heard of things called barometric pressure, or you've just seen barometers in stores. Well, here's what they are. It's a device for measuring atmospheric pressure at a particular time and place, and that place is wherever the barometer is. You take a tube, you fill it with mercury, and you turn it upside down in another container of mercury. The mercury will fall until the net force on it is 0. And what mercury are we talking about? The mercury in the tube, right over here. So let's see. Let's take one little mercury molecule there. And we know that gravity's trying to pull it down. We're going to sneak in a little free body diagram here. Now, what's atmospheric pressure doing? Well, here, let me erase this because I think we've indicated what we've got going. Atmospheric pressure, the entire atmosphere is pushing down like this. Now, once it puts pressure here in the container, that pressure is going to go in all directions and it will be perpendicular to every surface. So there's going to be a force trying to push the mercury up the tube. So here, that's your other force. That's the force of the atmosphere. So the mercury will rise until the force of the atmosphere is balanced by the mass of the mercury in the tube, or fall as the atmospheric pressure gets smaller. So the greater the height of mercury in the tube, the greater the atmospheric pressure. This force here pushes it up further before it's balanced by the greater mass of mercury in the tube.